the brown grasslands of California. With just one look, you can tell it's summer here. And every summer, when our annual rangelands are dry and unproductive, ranchers are challenged to provide high-quality green forage for their grazing livestock. Now, the solution is to use irrigated pastures in California's valleys, foothills, and mountain meadows. Unfortunately, irrigating those pastures generates runoff, and adding grazing livestock increases loads of bacteria and nutrients. It also erodes the soil, and in general, increases the risk of pollutants downslope in nearby streams. The good news is, many of the tools used by the pasture manager to maximize forage production are also useful for keeping any potential pollutants on the pasture and have minimal impact on downstream water quality. In this program, we're going to take a look at how irrigated pastures support the state's beef cow herd. Next, we'll go over the irrigation process, and then we'll get into water quality issues. Finally, we'll go through the management options to reduce concentrations of pollutants in runoff and adjacent streams. Now notice that I said options. There is no silver bullet that will solve your particular situation. Ranchers will have to select those pasture management options that will best fit their particular circumstance. As of 2006, there are approximately 700,000 beef cattle in California. Most of these cattle depend on a forage base of annual rangeland, privately owned irrigated pastures and meadows, and public grazing lands. Seed germination on California's approximately 14.5 million acres of annual rangelands occurs with the first rains in October and provides green forage through late spring in normal years. Annual rangelands typically provide 70% of the state's forage base, but during summer months, these lands are dry and provide relatively low-quality forage. In drier years, this can extend from late spring to early fall. Typically, ranchers fill the gap in green summer forage by moving cattle from annual rangelands onto irrigated pastures and meadows, or onto higher elevation public land managed by the U.S. Forest Service or Bureau of Land Management. California's approximately 1 million acres of privately owned irrigated pastures and meadows are a critical resource to allow ranchers to meet the annual forage demand of their beef cattle herd. They provide a short-term safeguard in those years with below-average forage production on annual rangelands, and they allow the flexibility needed to accommodate annual grazing constraints on public land. While many variations exist, there are three major types of irrigated pastures and meadows in California. They are valley pastures, foothill pastures, and mountain meadow pastures. Valley pastures are commonly scattered among crop fields throughout the northern San Joaquin Valley, the Sacramento Valley, and within northern California watersheds such as the Pitt River watershed. Individual pasture size tends to be less than 60 acres. The plant community on these pastures is commonly a mix of perennial grasses and clovers, with alfalfa sometimes included in the plant mix. Annual fertilization is rare, but does occur in some instances. While green all year, most growth occurs from March through October. Valley pastures are on flat ground with slopes less than 1%. They are commonly laser-leveled and checked or bermed to assure uniform flow of irrigation water over the field. They tend to be flood irrigated by gated pipe. Irrigation water is commonly delivered via ditch by an irrigation district and/or pumped from groundwater wells. Valley pastures are commonly grazed April through October. During summer months, they can have as many as 4 head of cattle per acre, but 2 head per acre is more common. Cattle are often rotated on and off these pastures during the summer to allow for pasture rest and regrowth following periods of grazing. Winter grazing is generally avoided, but can occur in dry years, and some producers who lack range may choose to feed hay on pastures in the winter. Foothill pastures are often found on the west slope of the Sierra Nevada mountain range, from Merced County north to Shasta County. They have generally been converted from annual rangeland and are commonly intermingled with current annual rangelands at elevations ranging from 100 to 1,500 feet. Individual pasture size tends to be less than 40 acres. The plant community on these pastures is commonly a mix of perennial grasses and clovers. Any fertilization of these pastures is rare. These pastures are found on slopes ranging from 3 to 20%. Foothill pastures are commonly flood irrigated from open ditch or gated pipe with water provided by an irrigation district. In some cases it is pumped. However, the vast majority of these pastures are irrigated by water delivered from higher elevation sources via gravity flow from reservoirs, stream diversion, or runoff from another pasture. These pastures tend to be uneven in both terrain and distribution of irrigation water. Mountain meadow pastures are typically found between 2,000 to 6,500 feet in elevation. These meadows tend to be naturally occurring riparian areas, with streams and/or large springs within them. The size of these meadows varies widely, from a few acres to hundreds. Dominant plant species in mountain meadow pastures are commonly native grasses and clovers, as well as wetland species. While these meadows have slopes less than 5%, the terrain tends to be uneven and have non-uniform distribution of irrigation water. Irrigation for these meadows has historically increased their size and the time they are green during summer. Irrigation for meadows adjacent to streams is commonly from the diversion of stream water out of the stream channel and into ditches along the meadow. Some of these stream-based irrigation systems have been in use since the mid-1800s. So those are the three major types of irrigated pastures and meadows in California. And as we just indicated, because each has a different terrain, they also have a variety of irrigation methods to help get the job done. So now, let's take a closer look at how water must be delivered from the source to the ranch and pasture. Each ranch will have unique limits on the volume, timing, and location of irrigation water delivery to the ranch. These limits will be based on existing water diversion or delivery infrastructure, irrigation district policies, water rights and the needs of downstream users, and restrictions to protect aquatic habitat and species. Energy costs can also be a big factor on the feasibility of on-ranch ground or surface water pumping to irrigate pasture. One of the first things to consider is this water new or used? Irrigation water delivered to pastures and meadows may be the initial use of that water. It could be water that comes directly from a stream that has not previously been used for irrigation. But it is common for pastures to be irrigated with tailwater. Tailwater is water that has already been used, running off an irrigated pasture or crop further upslope. In foothill and meadow pastures, it is common for multiple pastures to be irrigated in sequence, so the tailwater from one pasture is used to irrigate a pasture further downslope. This could happen over and over from pasture to pasture. First, let's take a look at what happens at the top of the pasture when it comes to distributing the water around. Once water is delivered to the pasture or meadow, it can be distributed by sprinkler or flood irrigation techniques. Flood irrigation is used on the vast majority of all three pasture types. In a flood irrigated system, using gravity flow, the water is distributed across the top of the pasture and allowed to flow downslope, thereby irrigating the pasture or meadow. Several methods are used to distribute water across the top of the pasture. Open ditch delivery is a common method to apply water to a pasture. Here's how it is typically done for irrigated mountain meadows and most foothill irrigated pastures. Water is diverted from the open delivery ditch by small cuts or channels in the side of the delivery ditch, which will allow water to flow onto the pasture and downslope across the pasture. Unfortunately, this is the least effective method to apply water evenly to the top of the pasture to achieve uniform application for the entire pasture. A vast improvement on open ditch delivery is the use of gated or slotted pipe and risers. These are much better at discharging water uniformly into the top of the pasture and initiate irrigation. Gated pipe and risers are commonly used on valley irrigated pastures, and some gated pipe is used on foothill irrigated pastures. Once water has been discharged at the top of the pasture, The challenge with flood irrigation is to achieve even distribution of water across the pasture. This is important to provide adequate moisture to recharge the soil in order to promote optimal forage growth across the entire pasture. Foothill pastures and mountain meadows are rarely leveled because cut and fill leveling methods do not work on the shallow soils in these pastures. As a result, water follows natural flow paths in the terrain. The unevenness of flow can be improved by irrigating just portions of the pasture at a time. This is referred to as dividing pasture into irrigation sets. This confines a significant volume of flow to a certain area, giving the irrigator some control over the duration and depth of irrigation. On valley pastures, sets are often defined by low berms or borders and checks in between the borders, which run downslope and confine flow. Irrigators will irrigate an entire pasture set by set. Water is rotated from one set to the next until the entire pasture is irrigated. The duration and amount of water applied to each set varies, based upon several factors. These could include the amount of irrigation water available to the irrigator at the time, the size of the set, and soil moisture and plant conditions prior to irrigation. The duration of irrigation for a set can vary from several hours on valley pastures to several days on meadows. Irrigation applications are every 10 to 20 days for valley and foothill pastures, depending upon recent weather and plant water use. In mountain meadow systems, there is usually some degree of irrigation rotation, but generally not as fixed or regimented as on valley or foothill pastures. Frequency of irrigation on mountain meadows can range from continuous irrigation for the entire irrigation season to rotation on a weekly or bi-weekly time step. So far, we've taken a look at how irrigated pastures support the state's beef cow herd, and we've covered the basics of the irrigation process. Next, we'll get into water quality issues. Before we jump into how pasture irrigation can impact water quality downstream, you should know that the information we are providing to you is based on numerous studies examining E. coli and nutrient and sediment transport in tailwater directly from irrigated pastures, as well as within streams running beside irrigated mountain pastures. These studies allow us to document the range and concentrations commonly found in tailwater. They also allow us to test the effectiveness of grazing, irrigation, and buffer or wetland management to reduce concentrations in tailwater. One of the techniques used to document the increase of pollutant concentrations downstream is to sample the stream water above and below individual pastures. This example shows how easy it is to detect that concentrations have or have not increased as the water ran off each irrigated pasture. Further information and documentation of these studies can be found at this website, which is also listed at the end of this presentation. The question at hand is, how can pasture irrigation impact water quality? It is important to note that not all irrigated pastures impact the quality of downstream water bodies, such as streams and lakes. Each pasture must be evaluated to determine if it has the potential to generate negative or positive downstream water quality impacts. Irrigated pasture or meadow management could negatively impact streams in two primary ways. First, removing too much water from a stream for irrigation of foothill and meadow pastures can reduce the remaining flow in the stream to critically low levels. Reduced in-stream flow can reduce a stream's capacity to buffer inputs of pollutants and solar radiation. That can lead to elevated pollutant concentrations and water temperature. Second, tailwater from all types of irrigated pastures and meadows can transport contaminants from the pastures and irrigation ditches directly to the stream. Contaminants such as sediments, nutrients, and microbial pathogens can be higher in pasture runoff than the stream receiving this runoff. Pasture runoff can also be warmer than stream water. We will discuss these primary pollutants of concern for irrigated pastures and meadows: microbial, nutrients, and sediment. Now, one of the leading water quality topics for California and the nation is the human health risk associated with contamination of surface waters by microbial pollutants. Microbial pollutants fall into two categories. They are indicator bacteria and pathogenic organisms, that is, those that cause disease. Although pathogens are the underlying concern, most state and federal freshwater quality standards are based on indicator bacteria. Indicator bacteria include fecal coliforms and/or a group called Escherichia coli or E. coli. The presence of these indicator bacteria in concentrations above the water quality standard is assumed to be correlated to the presence of at least one type of microbial pathogen, which we will get into in a minute. While there are others to choose from, we will focus on the indicator bacteria frequently in the news, E. coli. Concentrations of indicator bacteria are measured in colony-forming units, or CFU, in a 100 milliliter of water. Most water protection agencies are moving to adopt EPA recommendations for an E. coli standard of 126 colony-forming units, or CFU, per 100 milliliter of water, for an average of 5 samples collected over 30 days. For a single grab sample in streams and water bodies, 235 or fewer CFU per 100 milliliter is the acceptable standard. Let's forget about water for the moment and talk about where E. coli comes from: fresh manure. We have found indicator E. coli concentrations in fresh manure from beef cattle on irrigated pasture and rangelands in California from 500,000 to 5 million CFU per gram. Now, given that a mature beef cow on irrigated pasture excretes between 30 and 60 pounds of fresh manure each day, that is a contribution of 6.8 million to 1.4 trillion indicator E. coli per day to the pasture. You don't have to be a gambler to know the odds are pretty good that some of those bacteria will end up downstream. Getting back to water quality, studies have indeed found cases where indicator E. coli concentration in irrigated pasture tailwater is above the EPA recommended standard of 235 CFU per 100 milliliter. The second group of pollutants that affect water quality are nutrients. Nutrient-based water quality concerns focus on the amount of nitrogen and phosphorus contributed to a stream, or a river, or a lake. If excessive levels of nitrogen and phosphorus are contributed to a water body, it can stimulate excessive algae and aquatic plant growth. This excessive vegetation can clog waterways, but most importantly, algae and aquatic plants consume a large amount of oxygen in the water. The result is lower in-stream oxygen levels that threaten the survival of fish and other aquatic organisms. The amount of nitrogen and phosphorus required to stimulate algae and aquatic vegetation growth varies from stream to stream and over the course of a season and across years. Sources of nitrogen and phosphorus in tailwater could be fertilizers added to the pasture or from plant materials consumed and excreted by cattle in their urine and feces. Over-fertilization or fertilization immediately prior to irrigation can contribute to high nitrogen and phosphorus levels in tailwater. Both of these actions are wasteful production practices. The majority of nitrogen in tailwater is likely from cattle manure and urine. Approximately 75% of ingested nitrogen is excreted by cattle relatively evenly between urine and manure. Much of the nitrogen is in the form of urea, which is quickly absorbed or used by pasture vegetation and soil microbes. Approximately 98% of ingested phosphorus is excreted by cattle as manure and is readily absorbed by pasture soils. Since phosphorus is typically strongly bound to sediment and soils, excessive erosion from a pasture would increase phosphorus concentrations in tailwater. So when it comes to finding nitrogen and phosphorus in tailwater during irrigation, it is likely from 1. Fresh fecal pats and urine spots deposited across pastures, 2. Fecal pats and urine deposited directly into tailwater ditches, and 3. Erosion and sediment transported during irrigation. And finally, the third pollutant that affects water quality and negatively impacts downstream resources is sediment. What problems do excess sediment cause? One example is what happens to the eggs of spawning trout and salmon. When the fish lay their eggs in gravels of many streams receiving tailwater from irrigated pastures, the eggs may be covered by fine sediments, or the pores between gravels become clogged with sediment, which can prevent oxygen reaching the eggs. Sediments can also fill in pools, which trout and young salmon use to escape both predators and warm summer temperatures. Nobody wants to swim in or drink murky or turbid water, so elevated sediment concentrations can degrade the aesthetic values of water. Finally, erosion of pasture soil leads to eventual loss of soil and therefore pasture productivity. Those are some of the problems sediment can cause. Where does it come from? Potential sources of erosion and sediment within pastures are cattle trails in the pasture and erosion in the ditches collecting and transporting tailwater from the pasture. This can be made worse by high irrigation application rates and the resulting increase in runoff. Excessive grazing can increase the amount of bare ground on the pasture and thus the opportunity for sheet erosion. Now that brings us to the question, what can be done about these pollutants from irrigated pastures and meadows? What are the management options to reduce concentrations in tailwater and adjacent streams? Fortunately, there are numerous management options to help reduce microbial, nutrient, and sediment concentrations. Equally fortunate, a management practice that is effective for one of the pollutants we've talked about is also effective for the others. Keep in mind, combinations of the management practices we are about to present can and should be used to protect water quality. Some, but not all of these options are feasible for all pastures or ranches. Selection of a management practice or combination of practices must be made with regard for the unique constraints and opportunities of each pasture and ranch operation. The management must account for the manager's production goals. In general, management options fall into two groups. Source control, meaning those that keep pollutants on the pastures or out of the tailwater, and mitigation, or those that clean up tailwater prior to discharge to receiving waters. We'll begin with source control. The manager controls the number of livestock and timing of grazing on a pasture. The manager also controls the rate, duration, and timing of pasture irrigation. Each grazing and irrigation management decision represents the potential to either increase or decrease the concentrations of E. coli, nutrients, and sediment in tailwater. The amount of grazing pressure placed on a pasture is a critical management factor. Stocking densities of 1 to 2 cattle per acre for a few weeks followed by several weeks' rest from grazing to allow plant regrowth are commonly sustainable. Greater stocking densities can be sustained, but shorter grazing periods and longer rest periods are required for the long-term health of a pasture. As grazing pressure increases, so does the cattle manure and urine load applied to the pasture. This means more E. coli, nitrogen, and phosphorus available for transport in tailwater. In a survey of 10 mountain meadow pastures, we found significant increases in E. coli as the grazing pressure increased. This illustrates this relationship and indicates that E. coli levels increase dramatically as stock densities rise above about 1.6 cattle per acre. Similar results for nutrients have been observed. Not only does scheduled rest for a pasture from grazing, that is rotational grazing, benefit the overall health and productivity of the pasture, it also reduces the load of pollutants available for transport. As cow pats age, they dry and become resistant to erosion by irrigation water. Thus, pollutants become trapped within the fecal pat. Also, readily available nutrients in fecal pats and urine spots are quickly taken up by plants and microbes. Bacteria and pathogen counts decline quickly due to mortality. At a minimum, managers should strive to rotate cattle out of pastures before irrigation events. In a survey of 10 mountain meadow pastures, we found that E. coli increased when cattle were in the pasture compared to no cattle in the pasture during irrigation. As the number of days rest from grazing increases prior to irrigation, there is a significant reduction in sediment, and nutrient and E. coli in tailwater. This illustration shows sediment concentrations in tailwater from Foothill Pastures rested from grazing 2, 15, and 30 days prior to irrigation. Excessive tailwater generation can occur from excessive water application rates. As the depth and velocity of flow increases across the pasture and through tailwater ditches, the capacity for eroding and transporting soil, fecal material, and pollutants increases. Water should be applied to a pasture at a high enough rate to assure uniform flow and irrigation of all portions of the pasture, but at a rate low enough to allow time for the majority of the applied water to infiltrate into the soil. Reduction of tailwater runoff can significantly reduce pollutants transport from pastures. For example, here you can see that as the tailwater runoff rate increased, so did E. coli observed from the Foothill irrigated pasture. Vegetative filter strips and wetlands can reduce microbial, nutrient, and sediment concentrations in tailwater. A filter strip is a band of vegetation that runoff from the pasture flows across before entering a stream or tailwater ditch. Wetland filters can be naturally occurring or constructed for the specific purpose of filtering tailwater. Vegetative filters and wetlands in no way guarantee complete removal of pollutants in tailwater, or even removal below levels of concern. The effectiveness of each filter and wetland is site-specific and is based on factors such as the filter or wetland size, the pollutant type, pollutant load, and runoff dynamics. For example, we studied the effectiveness of a small wetland to filter E. coli in tailwater from a Foothill irrigated pasture. During a dozen irrigation events, we found that the wetland was able to trap between 40 and 90% of the E. coli discharged from the pastures. Tailwater runoff rate was the key factor determining how much E. coli was filtered during each irrigation event. When runoff rates increase, trapping effectiveness was reduced to as low as 40%. This is because the filter is essentially overwhelmed by the pollutant transport capacity associated with high runoff rates. When irrigation application rate was reduced, and tailwater discharge thus reduced, we found that filtering efficiency reached 90%. Finally, the vegetation in a filter or wetland must be managed so that it remains a sink for nutrients. Grazing a filter or wetland at the same pressure as the pasture will not optimize filtering efficiency. However, periodic removal of vegetation is required to maintain capacity to sequester nitrogen. On Foothill Pastures, we found that a single cutting and removal of filter strip vegetation increased lead to 2.3 times more nitrogen sequestration than an uncut filter strip. Grazing of filters and buffers should be timed when runoff is low and soils are relatively dry. Grazing bouts should last only a few days. No more than 1 to 2 bouts per year are needed. In this program, we've taken a look at how irrigated pastures support the state's beef cow herd. Then we talked about the irrigation process. And next, we covered the water quality issues. Finally, we went through the management options pasture managers have to reduce concentrations of pollutants in runoff and adjacent streams. There is no doubt that irrigated pastures in California's valleys, foothills, and mountain meadows will continue to be a critical source of high-quality forage for grazing livestock ranches during the summer months when annual rangelands are dry and unproductive. Ranchers will need to select those pasture management options that will best fit their particular circumstance. The result will be continued viability of these agricultural lands and improvement of water quality in California's streams and rivers.